Hello there. Let's do DHCP and DNS because these two are just too useful to share a module with other services. So if you haven't already, do yourself a favor and subscribe to this channel so you don't miss an upload. Otherwise though, let's get into DHCP first. So let's start out with an overview. DHCP, or the Dynamic Host Configuration Protocol, has a simple purpose in our network, but a very useful one nonetheless. And that is to issue out IP information to client devices. And this is amazingly useful for end user computers, especially mobile devices. Now the reason being, if you do not use DHCP or any other kind of protocol service designed to allocate IP addresses to end user devices, you are going to have to do this statically. Now, considering most organizations usually issue their employees with a laptop as a work computer, that machine is going to come to the office in the morning, going to need an IP address for the workplace. But before that user goes home, you'd have to go and change the IP address to whatever the user is using at home if you were to use static addressing. But with DHCP, you can rely on the person's home router having a DHCP service and then a DHCP service running at the office to allocate an IP address appropriate to that end user. Now, it's not just an IP address that is provided, but also the subnet mask, the default gateway, and any other optional information that DHCP gives out, including DNS server information. So let's look at how the DHCP process works. And that involves a client and a server. Now what we're going to look at here is something called a flow diagram. And the more you get into networking, the more you're going to see these things. But we're going to have these two vertical bars just to represent the comings and goings of the traffic with some arrows in between. So it all starts out with a client being set to obtain its IP address automatically if you're using Windows, or DHCP if you're using an operating system and a settings menu that is not afraid to say DHCP. And the client will send out a broadcast called a DHCP Discover message. This broadcast is going to a destination port number of 67. Yes, DHCP uses UDP, so it's technically a UDP port number. Now, at some point, that discovery broadcast will reach a DHCP server or something acting as an intermediary between a client and a DHCP server, which we'll talk a bit about later in this video. And when that DHCP server receives that discovery message, it will make a DHCP offer. Now, the discover is basically, hey, I'm looking for a DHCP server. And the offer is a DHCP server replying saying, hey, I'm a DHCP server. I can sort you out with this IP address, a subnet mask. This will be the default gateway for your LAN. And here is a menu of all the optional information I can provide to you. The client will receive that offer on port 68. And then it'll make another message called a DHCP request. This will be saying, hey, I would like to use that information you provided, that IP address, mask, and gateway, and I would also like the following optional information from you. And the server will then acknowledge that, saying, cool, I set aside that address, you're the one who's using it, it's now yours for the time being, and here is the extra information you are interested in. So that is the for exchange message that DHCP uses. Discover, offer, request, acknowledge. Now in terms of setting up a DHCP server, let's check it out. First of all, you can either use a proper server or your network appliance. Usually we would use a router to do this. Whether it be a small office home office router or an enterprise router, it can still work. One of the key differences though will be that if you're doing it through a small office home office router, you'll probably be doing the setup through a web console, whereas an enterprise appliance, 50-50 on whether you have a web console or a command set that you have to go and run to get a DHCP service working. But one of the key things will be that the DHCP server gets a static IP address. You don't want this thing having an address that changes all the time. But it is normal for us to assign static IP addresses to servers for predictability, but doubly more important for something that's going to be giving out dynamic addresses. And then we will hop onto the server and create some IP address scopes. Now, depending on the vendor, they might refer to this by another name, like an IP address pool. It'll be the same thing regardless. It'll be a range of IP addresses that will be issued out to requesting clients. Now, I will say this a few times in this video, but the range of addresses that get issued out does not have to encompass the entire IP subnet. You can start the range later into the subnet or end it before the last valid host address. You will also, in that scope, be setting up the subnet mask that those machines getting the addresses will be using, as well as the default gateway for that IP subnet, and the DNS server address as well, or multiple DNS servers, which would be beneficial. Now, technically DNS server address information is considered part of the optional information, but it is just too useful not to include and use in your scope's settings. And then any other information that can be included. Now, the other optional information that can be included varies depending on what you're up to. But for example, if you're using voice over IP telephones, it might be the IP address of the SIP exchange server that you use to do voice over IP calls. If you are doing wireless LAN management with a wireless LAN controller, it can contain an option that indicates this is the IP address of the thing that controls wireless access points for a DHCP scope set up specifically to allocate addresses to a wireless access point. As you get further into networking and start doing more advanced things, you're going to come across some pretty cool options that DHCP can handle. And then finally, the lease duration. Now, the lease duration is because the IP address information allocated to a client is not permanent. It is basically like renting a property. You don't own it, you don't get to keep it forever, but you get an agreement between you and the landlord that, hey, you're going to live here for this period of time. Similar thing happens here with a DHCP server. The client gets the address for a period of time that the server states. And the client, if it is still using that address at the time the lease is coming up for expiration, the client can renew it, going on for another period of time. Now, some more interesting things we can do with the DHCP includes reservations and exclusions. First up, let's look at the reservation. So the reservation, an address from the scope, can be associated with a specific MAC address. This means that the reserved address is still part of the scope, but will only be allocated when a client with the specified MAC address comes online and makes a request. This can be amazingly useful when you want to ensure that a certain client keeps getting a specific IP address. Now, would you do this for every client? Not really. You do it on a small scale maybe, or for important systems to be sure that its IP address is very consistently allocated to that device. I will let you figure out any potential special situations where that would be useful to you. Then, exclusions. Now, an exclusion will be an address from the scope that is not allowed to be given out to a client ever, even if the whole scope of addresses has been used up. Now, this can be used to ensure that an IP address can be set statically to a device where that address was originally part of the scope. Now, this is normally only done when you need a static address, but it turns out that address is between the first and last address of the DHCP scope or pool. Best practice usually is to leave some addresses out, either at the beginning or the end of the scope, so that you can assign those statically, whether that be for the gateway, which you should make sure is left out all the time, a server on the LAN segment, a network connected printer, or anything like that. It's always good practice to leave between 5 and 10 addresses available for static allocation. Then comes one of my favorite things, DHCP Relay. This is more of an enterprise router feature. You wouldn't really use this on a home network unless you've gone a little bit crazy with a home lab. And what this will do is it'll allow a router acting as a default gateway for a LAN to be able to see DHCP traffic and relay it back and forth between the client and the server. And this can allow an organization to have one central DHCP server for the whole network, which is a lot better than letting multiple routers be DHCP servers for their respective LAN segments, because it makes life a little bit easier to manage. You have one central server rather than many little ones all over the show. And it might come with a different name depending on the vendor that you get your router from. For example, Cisco calls it IP Helper. So let's have a look at how it'll work. In an enterprise network like this, where we've got multiple LAN segments, each having their own dedicated gateway, I can go and have one central DHCP server located elsewhere in the network. And on each of these routers acting as a gateway for their respective LAN segments, I can go and configure a DHCP relay service. I would have to probably do this on specific interfaces, so it would be these interfaces in particular that I would configure it on. And what will happen is when that interface sees a DHCP discovery, what it'll do is it'll relay the discover message to the server. The offer from the server will then be relayed to the respective client. The request will be relayed, and so will the acknowledgement. And as I said, this makes life a lot easier, as this one server can have many scopes that deal with all of the LAN segments in question. Then, a very useful thing called DHCP Snooping. Now, most people will refer to DHCP snooping as a security mechanism for DHCP, and the goal of it is to prevent a rogue DHCP server from allocating address information. Now, we haven't really got heavy into the network security yet, but a rogue device is any device on our network that was not deployed by the IT department. Now, that device could be intentionally and maliciously added to our network, or it could be accidental. For instance, you could have an end user bringing along a small office home office router so that they can have their own wireless access point, because they saw online that you can turn small office home office routers into wireless access points. And they plug it into a network port, probably an RJ45 wall block, and they got their own little wireless access point. Now, ignoring the wireless security concerns, because they might not have done a good job there, the average end user does not know that you need to change some settings, like changing your home router to be a wireless access point. Otherwise, it's going to try and spit out DHCP information out of the switch ports as well as the wireless interface. And this now means that you've got users on the network who might be getting their DHCP information from the wrong appliance. Now, if this was done with malicious intent, it would be because the attacker can then dictate to the clients who the gateway is, and that would be fantastic for an on-path attack, formerly known as man in the middle. Now, what DHCP snooping does is it allows a switch, usually, to monitor for the release of malformed DHCP messages. And if it's layer 3, it can keep track of which interface to trust DHCP traffic on, and which ones to block certain DHCP messages. Let's diagram it out for you. So first, let's have a network here. Over there is our legitimate DHCP server in another network segment. It's fine, doesn't make a difference. And this switch over here is going to be doing the DHCP snooping for us. Now, to make this interesting, let's introduce that rogue DHCP server we spoke about in red, or orange, or peach. Now, what I would end up doing on that switch over there is I would go and set one interface to be the trusted interface for DHCP. And it will be that one. The way we set it up is that interface will trust a DHCP server response arriving. So if it sees an offer or an acknowledge come in on that interface, it's cool with it. And then these interfaces we either specifically set up or we just leave it be, depending on how the network vendor does their config, and they will not trust a server responding. So if a discover comes in there, that's fine. That's normal on a non-server interface. But if we see an offer come in on any of these interfaces, that would be suspicious, and the switch can block it, meaning that this DHCP server would not successfully get its responses to these clients. If we get a request come in here, that's fine, because that's what we expect to see from clients. But if we see an acknowledgement arrive on any of these interfaces in red, it gets blocked. Only the offer and acknowledge can arrive on the interface that's been set up as trusted for DHCP. Now, that all being said and done, let's look at DNS. Now, with DNS, or domain name services, let's check it out. It is an open standard, and its job is to resolve names to IP addresses. And it can either be hosted on a public server, or you can host your own private server if you want to. This can also be referred to as internal and external, which we'll talk a bit more about later on in the video. Now, it can store host names. Now, the thing about a host name is it will be unique on the local network, and it will be assigned by an administrator, and it can be part of a larger domain name space. When it comes to storing domain name information, that's where we have to have globally unique domain names, such as an organization's website would be a domain name. And that usually has to be registered with an organization called a DNS registrar. Organizations like GoDaddy, for instance, are DNS registrars. Not a promotion, by the way, just name dropping. And the cool thing about the public domain namespace is it's got a hierarchical structure to it, so no one server needs to maintain all that information. Now, if we use a website like www.comptia.org as an example, what we have here is quite a few things. First of all, the www bit, that is actually the host name. Yes, there will be a server called www in CompTIA's network, or wherever it is they're hosting their website. And then the rest of it, that will be the domain name, the CompTIA.org portion. And those two things together give us what's called a fully qualified domain name. Now sometimes you will see some / stuff coming over here. That is usually referred to as the page extension, where you might have / this page, / that page.htm or HTML. Sometimes you might have a PHP query there for a web application. You'll normally know it's a PHP query when you see question marks, equals, and greater than, less than symbols. But don't worry about that too much. That's more for somebody who administrates the website. Now, let's understand the public domain namespaces hierarchy. First of all, we begin with a root DNS server. That dot that appears between the organization's name and the .com, .org, .net, .whatever, that dot is the root point. And there are a handful of very popular root DNS servers. You've got 1.1.1.1 from Cloudflare, 8888 from Google. There's quite a few popular root DNS servers on the internet. And they know of all the top-level domains. The TLDs, or top-level domains, will be the .coms, the .orgs, the .govs, the .nets, etc. And you might get some country-specific ones. For example, you might get .co.uk, .co.nz to represent the UK and New Zealand. And then below the top level, you will get a lower level domain or domains, where you could have, for example, YouTube and CompTIA within the com and the org domain. And then you might even have subdomains like store.comptia.org, where you can go and buy CompTIA textbooks and lab access keys without having to pay for full training. Again, not sponsored, just mentioning it. So that in mind, let's see how we could do some DNS name resolution. So first, we've got a private network over here. We've got a client, a private DNS server, small little router taking us to the internet, where that public DNS hierarchy is present. So first, let's do a query where the private DNS server would be probably your primary main DNS server set up on the client. The client makes a DNS request saying, hey, I would like to know the address of the following name. And if that server has that record, it will respond. Now, this would be a private DNS name resolution, which would probably resolve the name of something sitting on this network, a private local server. But what about when we want to resolve something on the internet? Well, there's two ways this relationship can work. First up, we could have this private DNS server set to do what's called a forward lookup. So the way that'll work is the client will make their request to the private DNS server, and it'll be for something on the internet. Now, that private DNS server may not have that public record, but it has been set up to go and query or forward the request to a root DNS server on the internet somewhere. So it sends that request to a root DNS server. And then the root DNS server doesn't know about store.comptia.org, but it does know about .org. So it sends the request to the .org DNS server, which does know about CompTIA. And CompTIA's authoritative DNS server knows about the store.comptia.org domain. And that will have the record needed for that customer. And now the response that contains the IP address of that server can start making its way back up. And then to the private DNS server, where the client gets their response from their DNS server. Now, the benefit of doing it this way is that the private DNS server can act as a little bit of a filter to make sure that no dodgy or weird domains are being queried. However, it does require a little bit of extra setup and a little bit of exposure of that private DNS server to public DNS server infrastructure. So a lot of organizations, for simplicity, will do something else. Now that something else will normally involve the fact you can have a primary and a secondary DNS server as a client setting. So if they make a query to their private primary DNS server and it responds back saying, sorry, no, I don't know that, then the client will go and check with the secondary DNS server to see if they know the IP address for a given name. So the request goes to a root DNS server. That root DNS server then goes and resolves like it did before, and the response makes its way back up the DNS infrastructure to the requesting client. Now, a DNS server can have quite a couple kinds of records on it. First of which is an SOA, or Start of Authority record. This is configured on a server that is meant to be the authoritative server for a particular domain namespace. It will also have an NS record or a namespace record configured on it as well, but usually those two records are configured as a pair. Now the idea would be, if I'm going to have a lot of my servers hosted publicly, I would then maybe host my own DNS server for public name resolution services. And as it's my server and my domain, I would probably want it to be configured as the authoritative server, where if any other server on the internet says, no, this is the IP address, mine is the authoritative correct answer, regardless of whether another server on the internet has the correct answer or not. Mine is the authority, mine has the correct information. That's the idea of an authoritative domain name server. Because for a domain you might want several DNS servers just for redundancy and reliability purposes. Then you get a host record. Now there are two kinds of host records you can have. You get an A record, which usually deals with the IPv4 address for a particular host within a domain. And then you get a quadruple A record to handle an IPv6 address tied to a particular host name. And as IPv6 will eventually become the de facto version of IP on the internet, it's inevitable that we will rely heavily on DNS to target and communicate with IPv6 addressed systems. You also get MX records or mail exchange records, which just handle the general domain name for a mail server. Then we don't have to worry about, do we do SMTP dot whatever, POP3 dot whatever, or IMAP4 dot whatever for a email host server. You also get SRV records, which are usually done to handle particular kinds of service records. You get PTR records, which are pointer records, and they are reverse lookup records. Essentially, it's an IP address pointing to a domain name. So you can go and type in an IP address and get the corresponding domain name, sort of like searching for someone's phone number and finding their name. Then you also get TXT records, which are just arbitrary text records. Originally, they were created as ways for DNS system administrators to leave notes for themselves and others, but have since then been co-opted by services like Sender Policy Framework and similar services. There are also other kinds of records as well, but this will be enough for CompTIA's Network Plus. Now, in terms of deploying DNS servers, you get what's called a primary or a main DNS server, implying I'm going to be talking about a secondary just now. Now, please be aware, this is not the client primary or secondary server settings. This is more a case of how the server is deployed. My primary or main DNS server is going to contain editable records that are in a read-write state, and would probably include the start of authority and name service records. And usually it is the first DNS server for queries to go to. And it is usually the authoritative DNS server for that domain, especially if it's going to have the SOA and NS records. And then you get your secondary DNS server, which will have all of its records in a read-only state, meaning queries can go to the server and the clients get the responses, but the records themselves are not editable on that server. What's happening is the secondary DNS server is getting its namespace records from a primary DNS server, which means that if anybody were to maybe try and attack and compromise a secondary DNS server, they cannot easily edit the records. And the main purpose for this is to help with redundancy and performance, as if you have most of your queries going to a secondary DNS server, they can normally handle the stuff and not be too much of an issue when it comes to lots of people making queries and access requests. and might be a very popular option for security, as anybody who does try and attack a secondary DNS server is not able to authoritatively change the record, which means that we can be pretty confident that the attacker has not somehow redirected our customers or users to a malicious site of their creation. And then you also get cache-only DNS servers. These are usually set up on a LAN, and their job is to store recent DNS queries to speed up response times. I myself have a cache-only DNS server sitting on my home network, and one of the benefits is, once I've done a query, if I do that query again in the next few minutes, instead of having to do that whole lookup on the internet, I've got a local copy kept nearby. What's also nice is my caching server is able to filter out particular domains as well, to reduce on the amount of web advertising I see when I'm browsing the internet. And one of the big benefits for us is it also helps us reduce the load on a primary or secondary DNS server if we run our own one, by cutting down on the constant repeating requests. And then the internal versus external deployment. External, also referred to as public, will handle public internet domain names and is usually managed by either a public provider or your internal IT department if you self-host your own authoritative external publicly accessible DNS server. And it's usually used for resolving an organization's public-facing services names to IP addresses. Then your internal DNS server will usually be used to resolve internal servers for local network users or LAN users, and is almost always managed by internal IT. It does offer some performance advantages, as the DNS server will be nearer to the clients, lowering on latency, and does have the security advantage of an internal server is resolving the names to IP addresses of internal services, requiring no public record, giving attackers one less thing they could learn about your environment. But that is all I need to tell you about for DHCP and DNS. Two super useful protocol services for modern networking, mainly because they deal with alleviating IP address allocation challenges and resolving names to IP addresses. Way too useful not to have. Almost any modern network you can imagine has these two services running on them. Now, we will be talking about some of the other protocol services that you would find, or application services that you would find on your networks, but we'll do that in a separate video, as those ones are, well, it depends on the organization in question whether they're running it or not. Nonetheless though, I'd like to say thank you all for watching. I really appreciate it. And if you have anybody that you know, whether it be a friend, family member, colleague, peer, etc., who would be interested in Network Plus, don't be afraid to share this video with them. Otherwise though, I will catch you in the next video.